Hey, Walter. Good to see you. Are you, well, I guess more people will join us just 1 o'clock, right?
Yeah, I assume so as well.
Awesome. Awesome. Week 7. So there's only 5 more weeks to go. And really only 4 more weeks of formal instruction. I have to check. I think we are not allowed. I think, yeah, maybe I should check. Well, I think we're not allowed to introduce new material in week 12. So which really means that, there's only 4 more weeks of possible instruction. Now, graphs and all, yeah, I think, yeah, that's for week 11. So that's okay. Yeah, graph. So, but which means in 4 weeks you have to get to graphs after having mastered pointers and trees and splaying. If you've completed quest number 4, splaying is easy. Okay, I can tell you. It looks very scary, like a crocodile, but it's a very docile crocodile. I just made the connection myself. So it looks scary, but splaying is a whole lot easier than the previous one, which is lazy, because and it's not by design. Actually, I found out by looking at student code and submissions and your forum postings. I found that more students experience difficulty in finding the minimum and finding the real minimum, and especially when the laziness criterion is introduced. So there's 2 different kinds of these dances that you have to do, and those are some difficult dances. So my take was that number 4, just like in 2B, number 4, I think, which was the koala with binary trees. What is it, binary trees or general trees? So that was the one of the hardest, I think, initially. And here also, I think the Mockingbird is probably a hard one, and then splaying is easy. But however, students have gotten really stuck in number 6 and 7. Okay, 8 is easy, 6 and 7. So you got to make sure that you got enough time for things like that. And shotgun approaches and also bursty approaches, they're not going to work. Okay, you guys everybody here is consistently working every day, but some of you are coming in once in a while, and then pulling all-nighters and trying to get quests completed in 1 night or 2 nights at most. And I can see, from it's just a whole lot of submissions within a very compressed period of time. And that's going to be working less and less. It may have worked in 2B, but I don't think it's going to work, especially since you're not getting participation points at all for people who do that. Just posting a note saying, well, last week was really hard because I had all these other things to do, and 1 or 2 lines like that, those kinds of posts don't get any points at all. So and may actually get deleted because they're not very informative or useful for other students. But having said that, all of you regulars are here now, and you're all posting, and a couple of other regulars, I think, who can't make it now, like Dean said he can't make it at this time, Arman, and then Aman has posted some questions in the green subreddit. If you can please take a look and answer his questions. I don't know if you've already done that, but if you have, that would be great. Okay, those also qualify for participation points for the week. So please do take a look at Aman's questions and help him out, because he's one of the students who is just persevering all the way through, right? Even though he could have just dropped and done all the things on his own time and come back later on, he said, I'm just going to stick around and keep going as much as I can. And so students like him are valuable in many ways. So I would very much like it if you guys can help him out and make him feel at home. Other than that, this week you're probably going to get ready to work on splaying. Yes. Yeah, and like I said, splaying is a whole lot easier. once you've done lazy trees, you have a feel for pointers and where to look. Yeah, it's basically where to look, because life is full of decisions. And as long as we know where to look, we're good. If we don't know where to go, we have an exponential number of choices in front of us and we're screwed. Okay, so developing an intuition for where to look, that is the core of, I think, what I'm trying to say. Again, just spouting out the top of my head, just realized that that I think is the core value of question number 4, is to say, okay, now I've got the basic binary search tree logic figured out in my head, so I know how to do this. But still, I just need to make sure that if I enter a new city and there's branching roads everywhere, when I get to a place, I should have a feel for which way I should turn, right? Just by looking at it. And that takes a lot of practice and lots of visiting other places. And so, but eventually you get a feel. And I think that once you're there, displaying is a piece of cake, okay? Because with displaying, all you're trying to do, if you're interested at all, is there's only 2 kinds of dances you have to and the overall goal essentially of displaying is that you have a binary search tree. If you have an unlucky sequence of inserts, it's going to be very bad unless you keep on balancing it. Yes. And if you're going to balance it, you got to, if you do AVL, AVL is a pain. I never liked AVL even when I was a student, and I still don't like it in many ways. And I let the libraries take care of it behind the scenes. But just this extra housekeeping or bookkeeping with these 2 variables that you got to update and keep, because your node can't be thin anymore. Yes. With AVL balancing, you got to keep height information inside of it, right? So whenever you have to have this additional payload that you have to maintain, in addition to stuff that you're already doing, that's your core requirement, that is added baggage, isn't it? That's like, when I travel, I like to travel light with my toothpaste and pajamas, right? But, but if you have to travel with all these other things and you got to maintain, everything has got integrity, it is a pain, isn't it? It's cognitive load or not, yes? Okay, all right. So AVL, however, the one benefit of AVL is that in addition to all the additional baggage you have to maintain, it puts you in situations where you can get more and more comfortable with pointers and making decisions, so that and 2 dances called rotations. And these rotation dances, and you can come up with any number of these, okay? But these are certain ways of rearranging the pointers after you have a feel, right? So you got to get a feel for rearranging pointers first with just binary trees and so on and so forth. And then and searching, right? And searching and inserting and deleting. After you have a general feel for pointers, the next place you go to is to say, well, okay, now I know how to shuffle pointers around. Now, are there any sequence of shuffling movements that make use, right? That have utility, right? Is that result in some kind of predictable move, right? So, I once upon a time, in a previous life, I used to have a friend who was a dancer, okay, and she used to make these incredible moves and stitch them all together and come up with a choreographed piece that is like a half hour long. And there are so many intricate pieces in there. And I used to think, how could she, remember all of this entire half hour piece? It's so complicated to me, anyway, to an onlooker. And she said something that I think is very similar to how we approach these things, is that, well, actually, what you see is a 30-minute piece, but in my mind, it's not 30 minutes, because, and then she broke it down. And then, it's basically spliced together many segments. So the only thing I have to learn is how to seamlessly join 2 segments, so that, at the conclusion of one, the next one follows, and then I can just seamlessly go so that people don't notice. Does that make sense? So she has learned a whole bunch of sequences. And then she said, you change the music, I can still dance to that tune, because I'll just have to shuffle these pieces around. Because the pieces now fit together differently and looks like a different dance, but it's just the pieces are now rearranged differently. And it was incredibly beautiful just to watch the transformation. And so the more important takeaway for me there was that, wow, that is exactly right. Once we learn how to manipulate pointers, then we can look at certain standard transformations of these pointers. to say, well, if I make like Rubik's Cube, how many guys have solved Rubik's Cube? I've never solved it. My son used to solve it like that, but I've never solved the Rubik's Cube, right? But if you look at the Rubik's Cube, and I look at all these expert solvers, they're essentially performing calculus-like steps, right? They're not really moving that red here and things like that. They recognize a pattern, and then they have in their mind a whole bunch of other patterns, and they know that in order to go from here to there, I have to execute a dance, which is L, R, R, U, B, N, N, R, R, right? And that basically translates into left, right, and whatever it is. Yes or no? Have you seen these Rubik's Cube formulas? Right? And Adam, one of my friends from back in the day at SRI, he's an expert Rubik's Cube solver, right? And he published these incredible things on online about minimum number of moves required to go from this transformation to that transformation, things like that. So every art piece is just basically like that. And so dance is basically just stitching together these incredibly beautiful little pieces that are self-contained, and then shuffle them in the right order. You can't tell it's the same, but it looks like a different dance. And so with pointer manipulation, right? So there are some, given that I have a playground, which is all binary, right? It's binary, right? And it has inbuilt rules like left and right, less and low, higher. Okay, that's all I know is playground. What are the dances I can perform in this playground that will take me from any situation that I have, any configuration of the playground, to another configuration of the playground, which is predictable, right? Now, predictable is the key word there, because if you go back to information theory, long before bits and bytes and everything like that, right? Predictability is the only thing that has value, right? Predictability is the ultimate Bitcoin, like energy, right? It is, if you can predict something, you can extract value from it. If you can't predict anything, there's no value. Right? And that's why, a uniform distribution, a uniform probability, which is also very hard to get, right? Because everywhere you look, there's information, because everything is a Gaussian at the end, isn't it? Everything is a sum of multiple, samples. So, but uniform distributions have no information, because sigma pi log pi is actually the maximum, right? And negative. Right? And so there's absolutely no information in uniform distributions. But once you have non-uniform distributions, when you have actually energy peaks, right? And then you see these things emerge, that's where you have the information. And when you have these peaks, then you can exploit them. Right? Computer scientists are not the first. Gambling houses were the first to exploit these, right? Because if you go back 100 years, 1,000 years, even millennia, back to China, ancient Egypt, and India, and Greece, right? They were gamblers, and they were people that analyze how to win these gambling games, and and rig these machines or whatever it is, right? It's been there all along. How long is chess and cards? You go back to ancient China. I'm pretty sure they were gambling with cards, long before civilization as we know it here was born, right? So so utility is ultimately in predictability. As soon as you can figure out some predictability that other people can't, you can narrow in on it and say that I can make money out of it. And so gambling houses basically make use of that essentially, because in their slot machines, this is my theory, okay? And this is how you can actually build a valid gambling. You shouldn't really go into gambling, because it's I think it's addictive and bad. But if you wanted to, right? Technically, if you are a really super duper good engineer, okay, the law, for example, will say, you should only have fair gambling machines out there, but fair cannot be 50-50 odds, right? 50-50 odds means the measurement has to be so accurate that current measuring instruments can't do it. However, let's assume that you have come up with an incredible measurement strategy, right, in which you can get to 50-50 odds within 0.0001, 9 figures of accuracy, right? 9 figures of accuracy. Whereas the government says, no human is going to get to 9 figures of accuracy, right? So you only need to, the gambling machines only need to be built with, 3 figures of accuracy, 99.999% fair. Yes? Because, you're getting 100% is impossible. So suppose by some incredible stroke of genius, you figured out a gambling machine in which the odds are known to you to be to 10 places of accuracy, right? Then you can actually exploit the fact that you have, the extra accuracy that is not required for this gambling machine to comply with fair standards. Yes? So you can exploit the extra information you get from that gambling machine. And therefore, even if the gambling machine is totally fair, right, you know when the house has to bet more, right? So on average, over millions and millions of tries, it'll work out in your favor because you have the edge. And I don't know where I was going. Yeah. Okay. So splaying is essentially that. Okay. So when you say that I have a tree, right, and after a particular dance, essentially it's a dance because you're going to close your eyes and say, I'm going to make a dance saying left go here, right go here, left child go here, right child go here. That's it. Okay, bam, that's your dance, right? And isn't that how dancers do it? Left foot, right foot, hand, and bam. Okay, so and they repeat that move and it looks like a dance, right? So you do that dance and then you say, well, after I've done the dance, can I have any predictive statement to make about the new playground? And you say, yes. Okay, if I perform this dance an infinite number of times, I can prove with mathematical certainty that the new playground is on average, right, has less height than what I started with. In fact, you can prove with just one of those dances you can, right? So it is a proof, right? It's a very simple mathematical proof that when you rotate it, the height actually decreases, right? And so if you can prove that, you leverage that instantly and say, well, now I can build a special kind of binary tree in which I don't have to suffer the lame ass overhead of those 2 extra bytes or whatever it is I'm using to track the left and right balance information, right? Instead, I'm going to provide a new kind of binary tree in which it's your plain old binary tree, no extra overhead, except that every time you insert and delete, you have to perform these dances. So when you keep performing these dances, each time you perform a dance, it is guaranteed to reduce the tree's height on average by this much. Okay, so that over an infinite number of times, it'll be better than logarithmic because the input, the way in which the data is distributed is non-uniform. It has a mode. Okay, it's not uniform, right? And the beauty of a splaying tree, and I think this was one of the challenges I gave extra credit for in a previous year, is that if the data is absolutely uniform, absolutely no information at all, then you can prove mathematically that over an infinite number of insertions and deletions, the average time per insertion and deletion is logarithmic. So that is the worst case when there's absolutely no information that you can prove. But is it the case? Is that the case? No. In reality, the case is actually much better than that. It is very hard to get uniform distributions, right? In fact, it's very, very easy to destroy a uniform distribution, right? The rand function in C++ or in the library, right, gives you a uniformly distributed number, right? It's equally likely which bin it falls into, whatever range you pick. However, newbies, I see them all the time. They want a bigger rand, they'll add these random numbers together, okay? That's the easiest way to screw up the randomness, right? It's not uniform anymore. Once you add up multiple distributions, it now becomes a normal distribution, right? It'll be peaked like a bell. So it's destroyed. So where I'm going with that is that it is actually very hard to keep information out of systems, right? Information just keeps seeping in, whether it's right information or wrong information, it doesn't matter, right? It always keeps seeping in. It's very hard to maintain the purity of the uniform distribution. And it's easy to destroy it. And but the advantage of having a non-uniform distribution, which is the most likely case of incoming data in most cases, is that you can use splay trees because it's non-uniform. On average, your access times will be better than log n, right? It won't. In fact, it won't be log n. You can prove that empirically if you have a mode in the data, the access time will be better than log n. So it's in fact better than AVL trees. Does that make sense? All right. Now, everything I said so far is basically just, there's no proof, and I was just pulling things out of air. Although, I've thought about it and we've talked about it in the forums before and nobody actually picked up on it. So it may completely be false. And maybe there's a mathematical proof or a corner case that I completely overlooked where you can actually prove that no, it's not the case. You're actually welcome to try that if you are, right? And maybe, who knows, it may result in a paper for you, right? A research paper even, who knows, right? So go ahead and try and think about these things. And so that those are the advantage of split trees. And once you're comfortable with binary trees and the lazy trees, I don't know, many people, I've never used a lazy tree in practice. Okay, so the whole idea with lazy trees, the assignment with lazy trees is essentially to just get you more comfortable with pointers and turning with your eyes closed, right? And making these dances more familiar to you. So binary trees you tend to build and use mainly because they're easy. I have never used a lazy tree in practice. And then you go to split trees, right? If you have a case where you think you want a balanced tree on average, you can just take an existing binary tree and add some methods to it and turn it into a, you don't need to add anything to the structure, right? And that's the advantage, right? You can take an existing binary tree from the STL library, and then you can make a split tree out of it, right? Instead of subclassing it to create 2 extra variables and a new node, right? Because if you wanted to take the existing binary tree from the STL library and then create an AVL tree out of it, it really is a pain in the ass, isn't it? Because you got to subclass the node, which is your building block of the binary tree, and add more variables to it, and you call it AVL node, right? Which has more information. Yes or no? Because you need height information and all that meta information for each node in AVL balancing. It is a real pain, right? I hate subclassing things and I try to avoid it as much as possible, right? And then the beauty of split trees is that it is clean, okay? And you love it. Once you, and in the past, okay, 2 years ago, I found, and this is my experience, okay, CS2C, students will, do all the up to lazy trees and they'll skip split and go to hash immediately, okay? And because, it's going to be one question, one lab, they think, okay, well, it's just split trees, I'm going to ignore it, okay? I know about trees now, I'll go on to hash tables. Bad mistake, if you ask me, okay? Split trees are really the crowning glory. After you've mastered AVL balancing, I think you can just finish it off and say, now I know exactly how the tree works, okay? I know how to throw things around. I know now not just to throw individual nodes around, I can throw individual whole branches around, right? I can just chop this off and throw it there because that needs to attach there. So you get the feel for saying, okay, this entire branch can go there. And because previously you're only playing with baby nodes, moving nodes around. Now with trees and lazy trees and so on. Now you get the tree, entire lop off entire branches, rearrange the whole tree, right? And when you're comfortable with that, then you can say you're a tree expert, okay? So I think when you're comfortable with split trees, you can go to any interview and they give you a tree problem. You can actually solve it. You don't need to go just before the interview and go through leak code problems and say, okay, I want to solve like 10 tree problems, 10 graph problems, 10 dynamic programming problems. This is total waste of time. Okay, the whole idea before going to any top class interview is not to master each problem, is to get a feel for what the problem is trying to solve. Right? So you shouldn't try to solve 10, but you should basically solve as much as you need to get a feel for what is it, right? So if you're solving tree problems, the idea should not be to say, I need to master 10 tree algorithms. You should basically be to say, I need to keep on mastering tree algorithms of gradually increasing complexity until a point where I get a feel for the tree, right? Which is basically, I know, right? Someone just throws me a random branch, I know where to stick it. That's it. That's all, okay? And a lot of students in the past basically get all the way up to lazy trees, okay? And then they will basically go easy on split and say, well, I'm just going to skip and go on to the next one, okay? And go to hash. And please don't do that. Please complete the split trees. It is actually an easy quest, and you can do it once you're comfortable with quest number 4. And it is actually a worthwhile quest to do, totally, okay? And so I'm happy. I'm happy that you guys are all progressed up to this point. Keep on going, okay? Keep going all the way, and I'm pretty sure you'll have a lot of fun. I can't wait for you to get to quest 6 and 7, and so and see the discussions you're having. Because if I go back, I see a lot of really interesting discussions from past Reddits in the quarters where there wasn't a huge amount of Reddit history. right? In the first couple of quarters, even though there were a few posts in the first quarter, I think the second and third time 2C, I ran 2C, many students didn't exploit the past posts, and they still made a lot of new posts. But then after that, I think reliance on the past posts became more. But now that I said in the syllabus, don't look at the past posts, it's actually back to square one. Not all students, unfortunately, but some of the active ones are actively contributing a lot of really new and interesting content, right? And sometimes new and interesting ways of stating what past students have done. Same thing, but stated in a new perspective, new way. All of those are beautiful, right? It's absolutely fantastic to see. So thank you all. So I'm looking forward to seeing more discussion like that. And you should always feel free to ask any concept level questions you have, and put together people to have that deep dive on concepts that. If there are 10 of you, right? I don't want this to be another one of these meetings. You're coming here already, but if there are 10 plus people who agree upon a difficult topic, just send me a note saying, well, we'd like to talk about, let's say, max flow, right? I think max flow is, I don't know why. Max flow is actually the easiest algorithm. Well, maybe, I don't know, right? One of the easiest. But yeah, if with 10 of us, we want to talk about this, can we have a class? Yeah, no problem. Okay, we can do it. Obviously, I won't give you the solution, but I can explain what the problem is in the first place, and also explain a couple of solutions which look really good, but they're not the best solutions, right? The one you have to code in the quest will be the best solution, but I'll also tell you a couple of solutions, and then you guys can discuss these solutions and say, well, I tried that, but it seems like it is, one order of magnitude worse, or, the constant term is worse than what I can do with this. Something like that, the interesting discussions, yes? And you can do that. Or you can also say, that really good is really good if I use a greedy approach to solve this problem, because the greedy approach, fewer code, fewer lines of code with greedy approaches, right? Because you don't have to do sophisticated logic. You just have to rank and pick the highest number usually. So you can say always people try greedy approaches first, because if it works, that's the best thing to do. And so so let's say we try the greedy approach. Let's say we try to do Crisco or someone, I don't know, is it Crisco? I don't know. Well, forget the name. What the algorithm I'm thinking of is minimum spanning tree. Well, you haven't done about, you haven't started talking about graphs yet, but you can turn every graph into a tree, right? Every graph you can turn into a tree by chopping off all the cycles and nominating a root node. Yes? So basically, a graph in which there are no cycles and you have a root node is essentially a tree, isn't it? Because you can go into it, and if you don't have any loop in the graph, that graph is fully connected because you don't have any disconnected nodes. So in graph theory, you'll find interesting ways to find out how can I take this graph and remove all the loops in it, so that, however, even though I cut out all the loops, I want to be able to reach all the nodes. So I don't want to cut. I don't want to make any city isolated. I don't want to blow up the bridges to make sure that city is cut off from everywhere else, right? I want to make sure that everything is reachable, but at the same time, I don't want to have any loops. Right? So army maneuvers, for example, right? So they're probably playing around with exactly the same kind of algorithms to say, how can I strategize these things so that, we can still access it, but there's no loop, so the other side can't access it, and things like that. And so you can computationally calculate that. If you're good in math and science and and graph theory, you actually calculate these. It's hugely valuable. And so you can say, so that's called a minimum spanning tree. And again, if there's many ways to get to a place and you want to say, well, these are expensive routes to maintain, so let me blow up all those too. I just want to keep the least expensive route to that place. So everything is connected, but I can get to them in the cheapest possible way. Does that make sense? So that is a minimum spanning tree, right? A minimum acyclic nodeless, disconnected nodeless graph, right? So, and how do you come up with one of those? You can do that easily, right? One way is to greedily say, I'm just going to, this is greedy approaches, right? This is greedy approaches. And if the greedy approach works, it's great. But let's say we do the greedy approach. And then you can take it upon yourselves to say, all right, I'm not going to calculate the complexity of the greedy approach. Or at least I'm going to prove that there's no approach better than the greedy approach. The greedy approach actually works and it's the best you can get, right? Those are interesting things, because once you can prove that some way of doing things is the best you can ever get, that's it. That's, you put the concrete on it. Even if an alien with super duper high intelligence comes to Earth, they can find a better solution. because you've actually put the logical lid on it. And so if you have a greedy approach and you can prove that there's no way you can do better than the greedy approach, then you can move on to some other interesting problem. You can say nobody can do better than that. However, if you can prove that, well, this is not the best, sometimes you can prove that too. You have an approach, a greedy approach, and it works, and it's not the best. So you say, well, that is n squared, but I'm pretty sure that theoretically I can prove that I can do that in n log n. So there must be something, something practical between the n log n, which is theory, and the n squared, which is practical, right? So there must be degrees of practicality here. So there must be trade-offs to get to the theoretical best. Does that make sense? And in fact, that is exactly what we do in information theory, right? Information theory, when we say, there's information out there, and the information you can calculate by saying with zero information when it's uniform, and there's this information when it's not uniform, and the amount of information if you quantify it in dash pi log pi, where pi is a probability of the event, right? You can calculate. So there's this much information here, this much information here. Now, however, this is the ideal, but I can't get that because there are practical constraints. So I'm going to trade off. I'm going to trade off by what is possible using today's engineering. Okay, so more and more engineering, nanoscale engineering, gets us closer and closer to the optimal everywhere, right? So engineering lets us get us better and better to optimal. And so you're saying in information theory also, say what is the most information I can extract out of anything with with the current available techniques. And that's exactly what we do, right? So even with algorithms, you say, is this algorithm as fast as possible? If I can prove that it's a faster algorithm, okay, can I reach it? So at least you know what to shoot for. I think that's what it is, right? Once you prove a mathematical bound, that's the importance of CS2C, right? Not 2B and 2A is a different level, as you know. CS2C is all concerned with complexity and essentially saying that can I prove it mathematically? Can I prove mathematically that you cannot do better than this? Because if I can prove mathematically you cannot do better than that, I can take my mind and apply it somewhere else. Otherwise, I can do this a little bit longer. That's essentially the reason, right? And so I shouldn't be blabbering on and on. It's already a half hour. So I'm sorry. I didn't mean to take up so much time. But since we were working on splaying and all, I thought I'll take a moment, especially since I had this challenge for splaying with extra credit. I'll still give, if you have interesting points to say about splaying and things like that, or even if you pick up, one of those past posts I made last quarter or the year before, here's this challenge for splaying. Yeah, I think I called it the croc challenge or something, just like you have the cormorant challenge. I think some kind of challenge. And you just make an interesting point about that, following on that from, or you don't have to refer to that, right? You can just say here's an interesting thing about splaying, and then say that. And totally, yeah. And that will get you extra credit points for doing things like that, right? That's over and above, going and helping people like Aman and 2B and helping your classmates in 2C and so on, right? You can also make insightful posts, and those may even get you more extra credit points than some of these things. So yeah, I'm looking forward to that, right? And those are things that will also be hugely valuable for yourself down the line. Everything clever and interesting you say now, you will value greatly, and because they'll also be, things that you can build off later on. Nothing you write now, which is truly valuable, will die. I can guarantee. Okay, anything you do that say in your forums that is actually valuable, you should just think of it as a seed. Okay, a seed that is tossed into a forest. Right, fertile land, and you don't have to care, right? It's just seed. You keep tossing these seeds around, and you don't care if all of those seeds are bad. Okay, the bad seeds are not going to germinate, right? But if you keep tossing these seeds around in this forest, some of them are going to germinate. It's just going to be slow. It's too slow for you to follow. Maybe 10 years down the line, right? That seed has resulted in this remarkable flower that someone points you at and said, "Hey, look at that! That is a result of something you said 10 years ago." Right? And so you have to take it on yourself to make your own future life fun, because at some point later on, all of you're going to say, well, you know what, there's nothing left to do. I can do anything I want. I can get anything I want. What's more? Okay. And those days you will find it's a whole lot easier to pass, and actually interesting too. If you say, well, you know what, and now that I'm retired, I'm not bored. because I have 15 years of creative work that I can just look back on. Even if other people aren't producing creative stuff, I just look back on what I did and say, hey, that's really cool. Does that make sense? And so these are all things that you can do right now. Bad things you can delete too, anytime later on. But there's no reason to come up with a brilliant idea and just toss it to the wind. Because how many times, you're going on a bike and you have an idea and you say, forget about it. So instead of forgetting about it at your age, just, record it, put it in a journal, in a public journal too, right? Because it shouldn't just be for you. Maybe someone else picks it up and says, hey, that's really cool. And they build on top of that, right? And then you can go back and say, hey, that's fantastic. That's really cool. Thank you, man. And so on and so forth, right? So all of these cool things can happen. So yes, just don't restrain yourself, okay? Because you can always delete what you say. Not that it even matters. Nobody cares about what you said, okay? Everybody cares about how you are in the current moment only. So just go ahead. Feel free to be yourself, and also, yeah, and pass this message on to the other people who aren't here, okay? Yeah, thanks. All right, and again, I just took that opportunity to launch your spiel. You guys should just feel free to talk. If you like, I can just turn the laptop around, unless you have a question for me. And then when you guys are done, you can just tell me and I'll just switch it off, okay? So is that okay? Or if you have a question for me, feel free to ask. Otherwise, I'll turn the laptop around. You can talk. No? Okay,
Actually,
right. So, yeah,
I
go
sort
ahead.
of have a question. Maybe Riley can answer as well. But just in case, I have a question about how the speed is changed compared to an AVL when looking at splay versus AVL, because the spec mentions, how AVL has that consistent log n speed for looking up, and it says here that that was sort of something that I was confused on. It says, we make sacrifices in order to have a thinner or lighter tree, and that we don't need to store all these things like the length of it. And my question is, how does that affect the speed? That's something I really haven't understood yet. I've just sort of understood the rotations and whatnot, but I do not really understand the speed of the operations compared to the AVL yet.
Yeah, before I'm sure Riley can, you guys can have a conversation with Riley and all the other people about this very soon. I want to say one thing before I turn over to you guys. Is that okay? I connected to what Walter just said. Okay, I just thought, as Walter was explaining this, I just thought of an incredible experiment you guys can do, right? Now, you want to measure the speed of working with an AVL tree with display tree. Now, forget about the space, okay? Space is not going to be a big issue here because we're not benchmarking on space and swap access and things like that, okay? We're just doing small trees, maybe, 1,000, 2,000 nodes, yeah? Okay, so we want to benchmark AVL versus Splay. And you can actually report this in our forum. You can also report this in Stack Overflow and all these other places. And this is an experiment I ran, and this is the output. I think it'll catch on like wildfire, okay? And people will actually find this hugely useful and maybe even cite it, I think, right? Because it's actually a real experiment. Please do this experiment if you can and post the results, right? And maybe check it out in the Reddit forum first, and I'll chime in, and other students can chime in, so you can refine it. And before you turn into a proper report, you can share on GitHub or on Stack Overflow, right? One of those places. Okay, here's what I'm thinking. What you need is to first implement AVL, which I think is you're going to do anyway as practice for splaying, right? So you're going to do AVL balancing. It's in the forums and it's in the modules. Implement AVL, a very basic AVL tree. You basically implement binary and then subclass it into AVL node and create the AVL tree. Okay, now you have a working AVL tree. Solve quest 5, so you also have a working splay tree. Two different things. Now you're going to benchmark the two and say which one is faster. How do you benchmark? Now, in order to benchmark, these are, I think, the steps, my recommended steps, and you can, fine tune and customize as necessary. I think that we want to have two trees. They're both trees of integers, right? Just integers, size t even, positive integers, only positive integers, so that that condition. It's both binary trees. AVL is going to keep it balanced, and display is also going to keep it balanced in its own way. Now you're going to generate numbers at random to insert into this tree, and you're going to generate, let's say, 10,000 numbers. Okay, so you will have 10,000 nodes, And 10,000 nodes, each node is 32 bytes, 32,000, 32,000 times 4. I don't know. This is still less than 100K, right? So we're not even talking about swap or big memory. 10,000 nodes. You're going to generate 10,000, maybe even 100,000. Who cares, right? You can figure out what the number should be. 100,000 random numbers. Use one invocation of RAND. Okay, just use one invocation of RAND. That's all. Okay, one invocation of RAND, and generate 10,000 numbers, and repeat that. Let's say 50 times. 50 times. Maybe you have to run it overnight in a batch script or something like that. You have to run it 50 times. So AVL tree with 10,000 random numbers, 50 times. This is how long it took each time to insert. Okay, just forget about nothing else. Just insert. Just insert. Now, when you call RAND, you use a fixed seed, right? Use your birthday or use 0 or whatever it is. You have to use SRAND with a fixed seed. Now, you want to do exactly the same experiment. Now, importantly, you have to use the exact same seed. Don't change the seed, okay? Because you want the same sequence of random numbers, right? And you're going to generate 10,000 of the exact same random numbers to this guy, to the display tree, 50 times. Now, remember, each time you 50 times, you don't call SRAND 50 times. You only call SRAND right once at the very beginning. Yes, because you don't want to do the exact same experiment. You want to do it for different sets of random numbers. So once you call the first one, you don't keep yanking back SRAND to the same pointer. Okay, SRAND should be the same. So you only call SRAND once in main, and then in main you're going to repeat 50 times. We can fine tune and fix these things in when you discuss your code in the Reddit. We can fine tune in these things. Okay, so you have the average performance of 50, over 50, average over 50 of the insertion times with AVL, right? An average 50 insertion times with display. Okay, and this is with the uniform distribution. Now you're going to turn that into a non-uniform distribution. And the way to turn that into a non-uniform distribution is generate a new random number, which is the average of 5 random numbers. Okay, an average of 5 calls to RAND. Okay, when you average 5 random numbers, it's not going to be uniform anymore. It's going to be a Gaussian. Yes? Now you're going to do exactly the same. So you're going to, instead of calling RAND, you're going to call my special RAND. Okay, and my special RAND is going to call 5 randoms, not 5 times random. Okay, 5 invocations of random, divide by 5 and return an integer of that. Okay, so you're going to call my special RAND instead of RAND. Now you're going to inject, not uniform numbers, but a distribution with one mode, and it only has one mode, not multiple modes. Therefore, in your display tree, you'll find that the mean of that distribution, you can generate the mean, obviously, right? Because the fixed seed, and you're generating the same numbers over and over again, you can just average that and find the mean, right? You'll find that the mean is actually very close to the root always in a display tree. But you don't have to look, right? Because ultimately you're not looking at the structure, you're just measuring empirically. So you can find out the average time taken with AVL trees, average time taken with display trees, if the numbers are uniform and if the numbers are non-uniform, right? With one mode. 2 different experiments, you report those numbers, it'll be like a super duper valuable experiment. Okay, now let's say that I will actually offer, I don't know, 10 extra credit points, right? 10 extra credit questing points to someone who does that exercise, but you have to complete your quest number, the crocodile, right? After you finish displaying trees, if you can do this, because you shouldn't take too much time. Okay, if it takes too much time, you'll quest number 7 and 9, you'll run out of time. But certainly it should take like less than half a day, basically chilling, right? After you finish 6, after 5, before going on to 6, you have some chilling time and you want to just play around. This is the experiment to do, right? So half a day's worth of work will actually get you some really, really cool extra credit, as also potentially fame out there. Okay, maybe based on the article, you get an interview call from some company that you want to work in, some group of people that that are doing some cool stuff, and say, hey, I want to work along with you guys for a couple of years. Okay, so maybe you get a call from them, who knows? So that would be a really nice experiment and report on. I have never seen an experiment like that. Okay, sometimes I look at forum posts from the folks who are doing the CS2C at Harvard and things like that, right? And many of the times they're basically talking about basic stuff. in the Reddit and Stack and stuff like that, or talking about Python and how to do data reading and input like that, they're not really talking about the meaty algorithmic aspects of CS50. Right. In fact, I see more meaty algorithmic discussion in our CS2C discussion on subreddits, on our Red subreddit, on some of these other forums. Maybe they have internal forums at Stanford and UCs where they talk about the interesting parts, but it shouldn't be it shouldn't be restricted, right? It should just be open like our subreddit, so everybody could see. But the problem is that there are open forums too where people talk about these things and they're not talking about interesting things, and it'll look like those courses are actually easy peasy courses, right? When people are basically just it's like how do I use a questing system in CS2C? That's it shouldn't be like that. So it shouldn't be like how do I do this in Python or things like that, or how does a basic chaining hash table work? Okay, more like quadratic probing and what's the value of quadratic probing over chain and things like that. So anyway, so that's basically it. I asked for a minute and I basically, like in India, we have the saying, let the camel put the nose into the tent. Eventually it'll just come in and push you out. All right. So I'm so sorry. Okay. So are you guys okay talking amongst yourself? Yeah. And I think that was an interesting experiment for you guys to do. I would actually be very interested in looking at the results of that. Thank you. Right. So if you need me, just call me. Okay. Otherwise, just talk amongst yourself. Any quest, even green quest is okay, because people will be talking and you can refer to Aman's post and say, hey, Aman, if you watch this video, I think this is what we think together needs to be fixed. Okay. Without giving the answer, you can say maybe that's where it's going on. Maybe someone can pull up the subreddit and talk about that. All of that is fine. Okay. Just have a free form conversation. Is that okay, guys? Just call me. Okay. Any other question? Also call me. I'm perfectly fine to come back. Thank you. Thank you. All right. Call me to end the recording too when you guys are done.
Yeah, so I think the main time difference probably between AVL trees and splay trees is just going to be in the accessing of recently used elements, because in the splay tree they all kind of gather towards the root. I think that's probably the biggest.
Yeah, that's what I was thinking too, especially just repeated lookups is where I can see the splay tree really sort of have an advantage over the AVL. And I also was thinking about something the professor mentioned, how if you look at a very small tree and you try doing the rotations based on what the splay wants, you do sort of get that idea that you get the sort of the middle ground, or it would be more like it will be the middle ground of your data set as your root node almost always. And that's sort of almost the goal, because if you have that, then it will be as balanced as possible. And it's interesting because it's also something that I've thought about during the last quest, because last quest we also did that we looked at, okay, let's go to the the right child, but let's find the smallest one there, or the left one and find the biggest one there. And we're not doing that different here in reality, just a different way of getting it through the rotations, which was interesting, because before I understood the rotations, I was playing around with the idea of just replacing things, but yeah, it's pretty interesting. The way we balance it was completely different than what I anticipated, actually. But
and
I was also I can imagine that for AVL trees, I mean, a huge part of it has to do with knowing the length of each one, right? And so it also seemed pretty extreme to me to keep track of something like that, especially when you're working with, if you're doing recursion like we did last quest. I mean, that's got to be really time consuming to go and figure out the length of everything. But yeah, that's the rotations have taken me a good amount of time to really understand. So I haven't really made the progress that I wanted to yet, but I'm hoping I'll get started soon.
Yeah, I finished left and right rotations. I'm still having trouble understanding the splay algorithm though. The modules are really good though. They have a lot of information on it.
Yeah, they're good. I was trying to make sense of some of the figures from the spec, and at first they were starting to confuse me a lot, but now that I understand, the two dances that you described and the rotations, it's starting to make a bit more sense. So yeah. Yeah, I mean, sorry, go
my
ahead.
bad. You can keep going.
No, go ahead. I had nothing to say.
Yeah, I was just wondering, are you guys interested in the 1 hour Zoom meeting about hard topics? Did you guys see the announcement from a professor?
Yeah, I saw it. I'd be down. I'm doubtful that we could get 10 people to attend,
Right. Yeah.
but yeah, I'd be down to join one.
So he said it could be about hashing, sorting, or machine learning if we want. What do you guys think?
Well,
I'd do any.
yeah. I mean, I think those meetings will become more and more useful in the later quests for sure. Personally, I think this one, I think sounds like we can figure it out. But yeah, definitely in the future, I would definitely want that. I mean, we can barely get 10 people to come
Yeah,
to
I
the
think
weekly
that's
meeting.
the
So
problem. Yeah. So do you guys think like getting from a CS 2A to B to C from all three courses, getting 10 people, would that be easier? If we talk about machine learning, something we can all learn about. Do you think
I think
that's
yeah,
a approach?
probably changing the meeting time, because I know Jason couldn't make it this quarter because of the meeting time, and a few other people talked about their full-time jobs interfering. So maybe if we shifted the meeting time, maybe we do another poll and ask about a time that can work for everyone.
Sure. Yeah.
yeah, I would be completely open to that. I think this meeting time was mostly chosen just because it was used last quarter as well. But yeah, I would be completely open to that. I have a pretty flexible schedule, so I'm able to change it based on what other people would need. But yeah, I agree that we could probably do something, those 1 hour concept meetings with machine learning. I'm not sure if it'll be as useful for CS2A with the sorting, just because it might be, I'm just trying to think back then. I don't know if I would really be able to understand that conversation at that point. But yeah, machine learning is something that I think everyone will be interested to learn about. Yeah, I mean, I haven't
My
got
bad.
far, so I don't have any questions. So if you guys have any questions,
Yeah. Are there any questions you guys want to talk about on the exam?
exam went pretty well for me. I had a bit of a scare the day before just because
Yes.
the practice midterm scared me a bit. So I did quite a lot of studying the day before. So which was probably good because I was happy with my result. But yeah, I can definitely help if anyone has any questions.
Yeah, I feel like it's easier than I expected because as I remember, CS2B has some hard exams for me.
I feel like it was like, because I feel like the CS2B exam was more about like the specifics of the language, and like there were like a lot of technical questions, but then like this exam is more about like concepts about algorithms and like trees and stuff, which is more like abstract, which is I feel like it's a lot easier to understand.
Right, yeah, I completely agree with that. The only thing I feel like I still need to work a bit more on is like the timing and big O notation, just because that was something I was still a little bit. I mean, most of the questions on the midterm were relatively simple, so I was able to get by, but that's definitely something I gotta focus on more.
Yeah, honestly, my score was a bit lower than I like wanted, because like most of the questions I just didn't really read them properly, and like I just kind of like there were like at least 2 or 3 questions where I got the right answer at first and then I changed it later on to the wrong answer. And then yeah, I just got kind of frustrated over that.
except for that, or should we just call it a day then?
Yeah, probably.
Hey, Professor, I think we're done.
Hey, awesome. All right, I'll see you guys on Monday, okay? I'll see you in the forums.
Okay, see you guys next week.
See you.
Bye.
See you guys
Thank you.
next week.